Hello viewers, I am Kausalya. Today's topic is obtain the transfer function of the electrical network shown in figure. Okay, this is one of the most requested video. So here, this is the basic diagram of a lag compensator. So I believe we all know about the basic components here, right? Here we are having a R and C connected in parallel and there is another resistor R2. And here the current flowing through this path is I of S and input voltage is Vi of t and the output voltage is V naught of t. Right. So here, as we all know, transfer function is nothing but Laplace transform of output to the Laplace transform of input. So here in this case, I am just transforming the elements that are available in the circuit in the form under S domain. So here this R1 remains the same, whereas C can be represented as 1 by Cs, right? And Vi of t becomes Vi of S and V naught of t becomes V naught of S. So this is the first step in solving this problem. Now the next thing is, you see, here we are writing input voltage in the form of, okay, I into R here. So what is the current that flows in this circuit? It is I of S, right? And what is the value of resistance here? So here the value of resistance is, we are having these two elements in parallel, right? And this combination comes in series with this resistor R2, right? Therefore here the total current is I of S, that is V is represented as I into R here. So this is your I and this entire thing forms your R, right? So here they are connected in parallel. So the combination is, you see, R1 into 1 by Cs divided by R1 plus 1 by Cs, right? And this combination is in series with this resistor R2, therefore plus R2, right? Now again we are simplifying the terms. So here, when you take LCM, you see R1 by Cs divided by, when you take LCM for this part, R1 Cs plus 1 divided by Cs here, right? So these denominator terms cancels each other and this plus R2 remains the same. And again, when you rewrite the above expression, you see R1 divided by 1 plus R1 Cs, right, plus R2. Again, this represents a single term, right, into I of S. Right, so we have represented Vi of S in the form of an expression like this. Now the next thing is, we are going to represent our output voltage. So here this output voltage is nothing but the voltage that is impressed across this resistance R2, right? So V naught of S can be represented as I of S into R2 because I of S is the current that flows through this circuit, right? So V naught of S is written as I of S into R2, right? Now we know the value of output voltage as well as the input voltage. Then what is the transfer function? So here the transfer function is nothing but it is the ratio of output voltage to the input voltage in S domain. So here both the terms are in S domain. So V naught of S is nothing but I of S into R2 divided by V I of S is nothing but this expression, right? R1 by 1 plus R1 Cs plus R2, okay, into I of S. So what happens? The I of S cancels each other and here the final expression is in this way. R2 by R1 divided by 1 plus R1 Cs plus R2. Right. Again, when you take LCM, that is LCM is taken first for the denominator part. So what happens? R1 plus this entire term gets multiplied with this R2. So here you see we are multiplying and finally in the denominator we are having 1 plus R1 Cs. Right. So when you simplify, you see finally here we are getting an expression like this. Right. Again we are multiplying this R2 with the terms here and similarly this R2 with the terms here. So finally the transfer function for the given electrical network is given as V naught of S by Vi of S, which is equal to R2 plus R1 R2 Cs divided by R1 plus R2 plus R1 R2 Cs. Right. So here this is our final transfer function for the given electrical network. Right. So here comes the end of this video. If you have any doubt, let me know in the comment section. Thank you.